Swayam Prabha. Digital India. Educated India.
Okay, so what we have seen, right, is a somewhat different implementation of first visit Monte Carlo. Okay, so the most common natural way to think about it is you just average the episodic rewards, but we can actually implement it in a slightly different manner where all we need to store, right, is the current estimate we had t and t itself. Okay, if you have these two and you get your current episodic reward, you do this update, right? You can get your next estimate. Okay, we had t plus one, and alpha t. As long as you anneal it properly, this process will converge to v pi. Okay, so this kind of online implementation of the first visit Monte Carlo method is taking a step in the direction of more full-fledged reinforcement learning. So this is what's going to come up next. Okay, so what we're going to look at next is further refinement of the first visit Monte Carlo online update. Okay, that gives rise to what is called the TD0 learning algorithm. The core idea of TD0 is something called bootstrapping. Okay, so let's get familiar with bootstrapping. So at time t, let v hat t be our current estimate of the value function. Okay, so v hat t as an entry for every state that, based on what we have seen so far, is our best estimate of the value of that state. Okay, and then what happens is we do our usual thing, right? We start generating data. So let's say that this is how the next generated episode looks. So now the question to ask, okay, and this is really the central question, is at what point of time, okay, when are we in a position to make an update to v hat t? Okay, so let's particularly say it for state S2, right? We had v hat t before this episode started, and then you start running this episode. This is what's going to happen if you complete running the episode. When, right, can we update v hat t? So that question is answered in one particular way by what we've been doing so far, right? By first visit Monte Carlo, let us say. So with first visit Monte Carlo, what we will do is we'll wait for the episode to end. Okay, we'll see, we'll hold on until a terminal state is encountered. So at this point, right, we have the long-term reward, right? 2 plus gamma times 1 plus gamma squared 1 plus gamma cubed 2 plus gamma to the 4th 1, right? And then that's a sample of what you can get starting from S2. So you go ahead and make the learning update. I'm writing it down as an online update over here. Okay. I mean, on the previous slide, I think we wrote this as G, right? But for the reason that this is the Monte Carlo way of doing it, right? I'm going to call this long-term reward that you got from this episode as M. Okay, so this is nothing different from what we have done so far. We wait for the episode to end, take the episodic reward M, and then change our update to be 1 minus alpha times what it was plus alpha times the new thing. Okay, but the question is, do we really need to wait until the end of the episode? Okay, maybe not. All right, so imagine doing something slightly different. Imagine that we went from S2 to S3. Okay, stop right there. Are we not already in a position to say something about what happens from S2 based on the fact that we have seen S3 now? Okay, this is like a new piece of evidence. Of course, you might have seen it in the past, right? But this is again something that is freshly generated. So why can we not make an update right at the point of time that we have reached S3 from S2? Okay, without waiting for the end of the episode. So that is precisely what is being done by doing this form of update, where we are going to say that my estimate of the expected long-term reward, right? One sample, so to say, of the long-term reward. It's not really a proper sample, but one reasonable estimate is simply 2 plus gamma times what I currently believe to be the long-term reward starting from S3, right? So we already have that in VT. So V hat T, remember, is our estimates based on what we have seen up to time step T. So they might already be something reasonable, right? You looked at data to come up with this estimate. So at this point of time, right, you can either start at S3 and again generate data and see what is going to be the value of S3. That's what's being done by the Monte Carlo method. But on the other hand, right, without actually running it from there, you can just use what you already have, right? And that is, we had T of S3. So how is this update going to look? You're going to say that having reached S3, my new target, right, or new estimate of the value of S2, right, or one sort of instance of that is 2 plus gamma times value of S3, value being my currently estimated value. So that goes as B, okay, and alpha times that plus 1 minus alpha times the current estimate becomes our updated estimate. Okay, and the reason this is called B is because this, right, B is a bootstrap estimate. What we saw earlier was a Monte Carlo estimate. So why is it called a bootstrap estimate? What really is bootstrapping? So, I mean, I'm not English literature major, but bootstrapping is basically the idea that let's say you want to jump off the ground, right? You have nothing to push you, so you make do with what little bit you have. Okay, so maybe one thing that you can do is hold on to your own shoes, right? Your bootstrap, try and pull it up and see if that makes you jump, right? So the meaning is bootstrapping is basically using your own resources, right, what you already have, right, to try and make some progress. You can see that's precisely what's happening here, right? We want evidence, right, in order to update V of S2. We have little bit of evidence coming from the fact that we got a reward of 2 and then we went to S3, right? This is something that's from a freshly generated episode. So use that evidence then and there. And how do you use it? You take 2 plus gamma times your current estimate starting from S3 as that new estimate, right? So if you look at it, right, B, which is your new estimate, is depending on your old estimate, okay, and it is in this sense that it's called bootstrapping. Okay, so this is a very simple idea, right, but this really is a very significant departure from the Monte Carlo approach, right? It gets you an estimate much faster, okay, and as we go along, we will see that this small change, so to say, right, also has fairly fundamental difference in terms of what we end up learning. Okay, so what you will sort of converge to when you do bootstrapping, right, is quite different from what you will converge to when you're doing Monte Carlo updating. Okay, but this is important. Okay, I hope you understand what is going on with bootstrapping. You get another chance at understanding bootstrapping because it is put together inside a full-fledged algorithm, and this algorithm is called TD0. All right, so TD stands for temporal difference. So TD0 is an instance of an entire family of algorithms called temporal difference learning algorithms. And here's a pseudocode. So let's just go through this. So again, this is solving the prediction problem. There is a fixed policy pi that is being followed. And we start with any arbitrary initialization of our estimate of V pi. Okay, so let's call that we had 0 before anything has happened. Let's also assume that the agent is born in state S0. Here is what happens forever over time. The action that you take is taken according to pi. It might be deterministic randomized, but let's assume actions are being taken according to pi. So when you take an action from ST, you're going to get a reward RT, right, and next state ST plus 1 based on action AT. This is enough data for you to go and make an update. Okay, that's the whole point of bootstrapping. At this point of time, we've already got enough to hold on to, right, and do something about, right? So S prime is one atom of information about the world, okay, which we've seen afresh. So we go and update our knowledge based on that. And the particular update that we do is what we saw on the last slide. We're going to write it slightly differently, okay? So earlier we were writing earlier estimate times 1 minus alpha plus alpha times the new estimate. So the minus alpha here, right, has gone into the braces over here. Okay, so this is just convention. This is another way of writing the update. Vt plus 1 is Vt plus alpha times the new estimate or target minus the old estimate. Okay, and the new one being here R plus gamma times Vt of st plus 1. Okay, Vt was the estimate of the value function we had at time t. We applied to state st plus 1, which we now know based on the new evidence has been reached by taking a from state st. Okay, and for the other states, right, this is Vt plus 1 of st. For the other states, you just copy over Vt. Okay, so you don't have any new data about states other than st, right, just after seeing this. So just retain your old data. So although I'm writing down this step explicitly over here in the pseudocode, very often, right, we will write similar pseudocode without explicitly mentioning that for states that are not visited at time t, we copy over, right? It kind of goes without saying. It is the implicit assumption. Okay, all right. So, and this happens, right? So on account of having done this, we went from Vt to Vt plus 1. And then again, go to the next time step, right? From st plus 1, you'll take an action, go do the update, and sort of you do this forever. Okay, so this is the TD0 algorithm. Crucially, you can see that it's doing a bootstrapping update. Now, what are the moving parts in this update? All right, why did we write it in this slightly different form? So Vt of st, right, is our current estimate of the value of st under pi, right? We want to change that to something else. The new bit of evidence that we have, right, came because by taking action AT, we got reward RT and next state ST plus 1. So we are going to bootstrap, right, use our current knowledge of what happens from ST plus 1. That's a long-term reward of VT of ST plus 1 times gamma plus RT, right? So this is our new estimate, okay? And this new estimate is available because we have this one new transition, right? So one unit of time has elapsed on account of which we have new evidence. And if you take the difference, right, between the new evidence estimate and the old estimate, so R plus gamma times VST plus 1 minus VST, this quantity is called the temporal difference prediction error. Okay, so this was the old estimate, that's the new estimate. The difference between these two is, it has the semantics of being an error, right? Because something's not okay if these two things don't match up. Why is it called temporal difference prediction error? Because temporal is the word for time. Okay, so this is the error that you notice is happening because one unit of time has elapsed, right? And what you're able to say based on the new evidence, right, does not really match up with the old evidence. So this quantity will be non-zero, right, if the things don't match up. Okay, it'll actually be zero if these two things are exactly the same, right? Then the temporal difference prediction error will be zero, and Vt plus 1 will just be left as it is, right? It's going to be just Vt. But in general, right, there need not be zero. In fact, even once you converge, right, to the actual values, there will be some difference between, there will be some error, right, because things are stochastic, right? What you're seeing is a sample of the long-term reward, right? You're not sort of seeing an expectation directly as you might in planning, right? But that's okay. Okay, and alpha t plus 1 we already know is the learning rate, right? It's the sort of step that you're taking, length of the step you're taking in the direction of addressing this error. Okay, so you take a step in the direction of cutting out the error by adding that to Vt, that becomes your Vt plus 1. Okay, so it's sort of, I don't think I said it earlier, but it is sort of, it goes without saying maybe, right? Or it's proven, of course, that this way of doing updating, right, bootstrapped updating, will also have you converge to VPi in the limit. Okay, so as you get more and more and more data, right, you keep doing TD0 updates, you will eventually reach VPi. In terms of implementation, just one note. I have written down the pseudocode assuming that it is a continuing task. Okay, so this is the reason that T goes from 0, 1, 2 forever. You just need to make a minor change if you're doing this on an episodic task. Okay, so when we were discussing Monte Carlo, actually we were doing it with episodic tasks. But if it is episodic, you just have to pay special attention to the terminal state, right? So as before, we should always fix the terminal state to have 0 value. Okay, so if an update happens where st plus 1 is the terminal state, right, don't do whatever, anything fancy, just set value of terminal state to be 0 over here. Okay, and of course, if you go, so maybe if state 23 is a terminal state and you go from there to 24, I mean, there's no point doing an update from 23 to 24, right? It sort of is like updating the value of a terminal state. Rather, you just start with 24 and then look at what happens when you go to 25. Okay, so if you're going from S1 to terminal state to S2, do an S1 terminal state update where the value of terminal state is fixed to be 0. Don't do any terminal state S2 update. Okay, I mean, that's sort of the natural way of doing it, but I'm just making it explicit. Don't be left with the impression that you can only do TD0 on continuing tasks. You most certainly can also do it on episodic tasks. Okay, so this is a slide that really you need to get very familiar with, right, and comfortable with. So I think I'm willing to stick my neck out and say that if I have to pick one concept, one slide for the entire course, right, which is really characterizing reinforcement learning, okay, which is really the most central aspect of it. It is the idea of bootstrapping and the idea that you can run an algorithm like this that will actually converge to VPy when you're solving the prediction problem. So why is it that central, right? So this is also, I think, bringing to light why reinforcement learning is different from supervised learning, right? So if you had to do supervised learning, right, and you're solving the prediction problem, somebody would just tell you, right, that for this particular state, this is the expected long-term reward. Okay, they will actually associate state with label, and then you have to sort of just solve the association problem. There is none of this exploration that you need to do, right? The second aspect, right, is that we are not getting the supervision. Rather, what we are getting is actual transitions which are stochastic. Okay, so the Monte Carlo approach is, it doesn't matter if I'm not getting the expected value, at least I can get a sample of the expected value by running out the entire episode, right? In expectation, it will be the expected value, but I can make do with a noisy version of the expected value, which is the sample, right? So in some sense, you're generating a noisy label when you're doing the Monte Carlo approach and then associating that with state and doing the update. Okay, because it is noisy, you have to do the stochastic approximation, right? You can't really set value to be what you see, right? Because what you see is noisy, so you have to average it out or do the small sort of learning steps in order to get there. But then the question is, do we really need to wait for the end of the episode in order to make that update? The idea of bootstrapping is no, I'll make do with what I already have, right? So just give me one transition. Using that transition, I'll bootstrap off what I already know and do my learning update. So the sort of label that you're generating for yourself, right, which is noisy, and in this case, which is also biased, right, is this R plus gamma times V of next state. The point is, it doesn't matter. Okay, there is a little bit of truth in what we are doing, right? It's not completely bootstrapped to the extent that we can be going astray, right? So it is actually true that the environment generated reward R, right, and took you to ST plus 1. So that part of it is actually new, and that is trustworthy. What might not be fully trustworthy right now is your estimate of GST plus 1 right now. But that doesn't matter. Okay, the point is that doesn't matter. If you bootstrap, right, in this manner, you will still converge in the limit to optimal behavior. All right, so this is TD0, and you can see that this is qualitatively quite different from the Monte Carlo approach. Also notice that you can actually run this on continuing tasks, genuinely continuing tasks that are going to run forever. With Monte Carlo, right, you have to wait forever. You have to wait for the episode to end, which means, I mean, you'll not really learn anything till the episode ends, right? That need not be the case. Maybe one way of fixing Monte Carlo is once you have enough data, right, that beyond a point, right, the contribution to the value is very small, let us say. Right? Then maybe you can just terminate and then do a Monte Carlo update, modulo a little bit of truncation error, right? So maybe you can, but conceptually, right, there's nothing stopping you from running TD0 as it is on a continuing task. Okay, so now the natural question, right? If you do TD0, right, what is it going to give you? Like, With Monte Carlo methods, it's kind of clearer that we are looking at an average, right? We know like what we're getting, but what really are we getting when we are doing bootstrapping and doing TD0 type of updating? In order to answer that question, let us first settle the matter with Monte Carlo methods. Okay, so as before, the same running example, you have, let's say, 5 episodes of data. What are we going to compute as the estimated value of each state, right? After t episodes, using first visit Monte Carlo, you look at the first occurrence of the state in each episode, look at the G, right? The long term return starting from there, and average all of those. And that's going to be your estimate. So consider this. Suppose we define the following error function. Okay, so for any estimator V, okay, of the value, we look at the squared difference between V and the actual long-term reward at all those points which are actually first occurrences of S. Okay, so every time that S occurred for the first time, right? So suppose you're doing it for I don't know, S1, right? S1 occurs first time over here, and then first time over here, and then first time over here, unless I made a mistake. Okay, so that's 3 occurrences of S1. In each of those, there is a long-term reward. There's also going to be a estimator V, right? So let's look at the difference between these two things. Square it, add it up, okay, and let's call that error, the error first of V for state S, okay. Now, because our prediction is the average, right, of all those actual long terms, it's not very hard to see that what we are outputting as the first visit Monte Carlo prediction, right, is the quantity that minimizes this definition of error. Okay, so we know that average minimizes squared error. That's precisely what is going on over here, right? So the answer that is computed by first visit Monte Carlo is the one that minimizes the squared error, where the squared error is defined as the sum of the errors, squared errors, where each squared error is the actual long-term return from a first occurrence minus the prediction. Okay. Every visit Monte Carlo is also doing something similar, right? It's again taking an average, but it's taking an average of a different quantity. It's looking at every occurrence of S. But again, that's going to be what minimizes the squared error, where squared error is defined as counting every occurrence of S. Okay, starting from there, you look at the long-term return. So every time S occurs, right? So let's do this for S1. It occurs over here, it occurs over here, it occurs over here, it occurs over here, and over here. Okay, so there are 6 or 7 occurrences. So there's going to be 7 terms in this error. Each time the long-term return minus the prediction, okay, for S1, the whole square, okay, summed up. Now, again, this is the average, and so this is the minimizer of this definition of error. So the natural question is, when we do TD0, right, is the answer that we get also, can it also be characterized by something meaningful like this, right? Is it minimizing some type of error? What is it doing? So we have to be a little bit careful for the following reason with TD0, okay? See, TD0 is a sort of properly online learning method where there is some initial V naught that we are starting out with, right? So imagine that you start out with some hat V naught and you do updating over, let's say, these 5 episodes, okay? So you only done a finite number of updates. So the answer that you have at the end of these 5 episodes, right, is still going to depend on what V naught was, okay? It's not going to sort of go away. Had you started with a different initialization, you're going to get a different answer. So what we're going to do is a slight trick, right, to ask, I mean, I want to get an answer that does not depend on the initialization. Let me do something with TD0 that resembles TD0, but that is sort of independent of the starting point. See, with Monte Carlo too, actually, you would have to do it had you done it in an online way with sort of different learning rate. What I showed you on the previous slides was what you get by actually doing proper averages, okay? But with TD0, we don't have that facility. We have to actually do something to get rid of the initial value. So what we do is actually quite simple and intuitive. So we've seen 5 episodes of data, right? So you start at the first episode, you start doing your TD0 updates, and you don't know what to do once you've reached the end of the 5th episode. So do the following: generate 5 more episodes in your own mind, okay? And do that by copy pasting your first 5 episodes and calling them episodes 6 through 10. So you've seen episodes 1 through 5. How do you go from this to having an infinite number of episodes? So in your mind, right, generate an episode 6, which is basically the same as episode 1. Okay, and 7 becomes episode 2, episode 8 is the same as episode 3. Once you're done with that, again 11 through 15 is going to be again the same episodes 1 through 5. So this is a way in which we are simulating an infinite number of episodes based on the data that we got just from the 5 episodes. Okay, and we will do TD0 all the way to convergence on this imagined infinite number of episodes. Okay, and when we do that, right, we will anneal the learning rate as before. We'll start with some initial V0, hat V0 estimate, and then keep refining it, right? And with time, right, you will actually be annealing the learning rate over and over and over again, right? So time actually keeps getting incremented as you go through these new episodes, through these simulated episodes. It's not reset, right, at the end of every batch. That would sort of defeat the whole purpose. So if you do this, right, if you do this an infinite number of times, then your answer will not depend on V0. And also note that it's only going to depend on the data that came from the first 5 episodes. Okay, there's nothing new that we introduced in this episodes 6 through infinity, right? It's just repetitions. And the answer that we get, right, at the end of doing this, let us call that V hat T batch TD0. Okay, so for natural reasons, this is called like a batch TD0 estimate because you've done it over and over and over again, right, on a batch of collected episodes. Now the question is, can we say something meaningful about this estimate, right? We were able to say that the Monte Carlo estimates minimized squared errors correspondingly defined. Does batch TD0 also minimize something or do something interesting?